Alright, hi, I'm Yash Pershad, and I'm talking to you today about HemaDrop, a technology to determine accurate blood composition via homogeneous thin solid films from microliter droplets of blood. I'm an undergraduate, and my research team is from Arizona State University in Tempe, Arizona. Our motivation for doing this research is the limitations of current blood analysis. So current blood tests require about 7 milliliters of blood per test, and there are some consequences of using such a large volume. First of all, for patients, for critically ill patients who have to undergo lots of blood tests, over time the amount of volume that is required to monitor a condition and diagnose their illnesses builds up, and over time this can cause hospital-acquired anemia. A majority of critically ill patients get this condition, and this condition is very bad for their health because it prevents their recovery since they have less oxygen in their blood, and then also it induces costs on the healthcare system since it elongates their stay. And then for a normal patient, a non-critically ill patient who's undergoing blood testing on a daily basis, maybe like one test in a year, individually, it can cause them discomfort like nausea, fatigue, and fainting, as many of you may experience when you get a blood test. And then another application for reducing the volumes of blood testing is in forensics. So if you're at a crime scene, potentially not that much blood will be available for use. So if you don't have a large volume of blood, you potentially couldn't analyze this blood without a new technology. So this creates the need for accurate analysis of microliter samples of blood, and that can address these issues. So since it's so important, previous attempts have been made at microliter blood analysis, and the previous attempts include one that's pretty well known, Theranos, and they use a finger prick method, which takes a nanoliter drop of blood from your fingertip, and then they use that to analyze information. However, there's a lot of controversy surrounding it, as you may know, and what was found out in a study by Kidd et al. In the Journal of Clinical Investigations was that they were simply taking nanoliter droplets of blood and then diluting it to the normal 7 milliliter amount, and then using normal analysis techniques for it. So what this did was diluting it introduced a 10% systematic error, which is above the accepted medical threshold. And for this reason, the FDA only approved them for qualitative tests, like detecting herpes, for instance, compared to quantitative tests where you can get actual concentrations of, for instance, iron or proteins in the blood. So our solution is fundamentally different than what is currently available with the large volume tests and Theranos, because rather than using blood in the liquid state, it uses blood in the solid state. So the reasons that we decided to pursue solid state blood analysis are twofold. So first of all, the solid film on the substrate allows for, if you have a small liquid volume, you can potentially spread this blood out, and it will create a larger surface area for analysis. So if you have a larger surface area for analysis, that's basically increasing the amount of blood you can analyze. Additionally, if you have a solid film as opposed to a liquid film, you have access to a variety of vacuum-based techniques compared to if you have a liquid. So additionally, solid blood will allow reduced volume, so 5 microliters, which is a vast improvement what's currently being used. And then, however, there's one major concern that people have with solid blood analysis, which is the uniformity of the sample. So if you're creating a film, you don't want the composition of the film to vary based on what location you are on the sample. So because let's say you're getting a blood test done, ideally you would not want the composition that you measure to vary based on what spot you decide to analyze. So using our patented method patent pending method in 2016, and then we have also a paper published in the Materials Research Society Advances Journal, we proposed the use of super-hydrophilic films beneath on a substrate beneath it to create this uniform film, and this research tests this claim. So to test HemaDrop, we used ion beam analysis, specifically Rutherford Backscattering Spectrometry, or RBS. And what RBS does is it analyzes elemental composition by probing the sample with helium ions, and this is in a vacuum. So you can see based on this apparatus, an incident ion beam is shot at the sample with an initial energy, and then based on how each individual ion is scattered by the sample, when it hits a target atom, a detector will detect its energy. So on an individual level, we can see that an ion beam will have an initial energy that we know, in our case, 2 megaelectron-volts, and then this projectile would be the helium ion, and then it's going to hit the target atom, so an individual atom in the sample, And then based on this, it's going to scatter. And if we can use detectors to measure the scattered ion energy. And based on this, using conservation of energy and momentum, we can find the mass of the targeted atom that it hit. So if we look at it from an ionic and atomic scale and blow it up, now we have an incident ion beam of many ions. And then using this, we can basically find the composition of the entire sample. And then that's the expression. So for our experiment, our goal was therefore to test HemaDrop's ability to create quantitative measurements, so accurate measurements, also show or find out if the film is actually uniform, so if composition is independent of location, and then also a major consequence, or a major concern that many people have with ion beam analysis in general is ion beam damage. So we wanted to see how the film would respond to being analyzed with an ion beam. First, for accuracy, the way that we checked the quantitative measurements would be to compare a film created by putting a drop on a HemaDrop substrate and a film used by using simply dry blood spot application technique, which is simply just putting a blood onto a substrate. Then to measure the uniformity, we measured on the HemaDrop films, we took multiple spots on samples and then multiple substrates. And with this, we could see whether the composition would overlap or would be identical depending on your substrates. And then finally, for ion beam damage, what we did, we took consecutive RBS spectra on the same spot and saw how the composition evolved as ion dose increased. To prepare our samples, we first applied HemaDrop coating to 2 substrates, and we applied our patented film onto the substrates to make it super hydrophilic. And then after this, we applied 5 microliters of canine blood. So we used canine blood because there are less strict safety regulations and we didn't want it to spread pathogens. So we used canine blood and we applied it to both HemaDrop prepared substrates and untreated titanium nitride substrates. And then finally, we let the substrates dry for 1 day before conducting RBS. So the reason we used had 1 day, we let it dry for 1 day is that we prepared the films on a Thursday and the ion beam laboratory is open on Friday. However, previous tests that we conducted show that it can also dry within 20 minutes. So the limitation is not time. And then all of this sample preparation or synthesis was conducted in a class 100 clean room, which means that there are less than 100 particles per 50 microns and greater than 50 microns in size per cubic foot. And then also we used biosafety level 2 guidelines in our laboratory. So here's some pictures of samples. In A, you can see this is simply a dry blood spot with no HemaDrop film beneath it. And you can see there's visible disuniformities and cracking, and you can see the substrate below at certain points. B shows a HemaDrop sample mounted in the ion beam accelerator, and you can see how it's not disuniform, and it's created a film. And then C and D show the 2mm by 2mm laser, and that's where the ion beam is going to hit the sample. And then finally, E shows the sample after ion beam analysis was conducted on it. So the spectra that we generated using RBS, on the left-hand side, it shows the spectra of substrates treated with HemaDrop, and on the right-hand side, it shows the spectra of substrates treated that are untreated, and we can see several visible differences. First of all, we can see that on the HemaDrop side, we can see that the leading edges for carbon, nitrogen, oxygen, chlorine, and iron are all very well defined and resolute. So this is how we can get quantitative measurements. And then on the untreated side, there's very little resolution, and you can even see the titanium leading edge right here, and that shows that the film is cracking and non-uniform, and that the substrate also matters, which is very not ideal for blood analysis. Additionally, it attests the uniformity of the HemaDrop samples because regardless of spot or substrate, the RBS spectra and elemental composition are pretty constant over time and they overlap with each other. And then also that shows the reproducibility of the measurements. Optically, we observed some damage with this indentation where the ion beam hit the sample. So for this, we wanted to use quantitative elemental composition and see how that evolved over time after we took the spectra. So to do this, we took 4 consecutive RBS spectra using 100,000 counts each, and that shows how the counts for each element scaled with the incident helium ion dose. So what we can see here is that the lines are either are horizontal or within the error bars. So we can see that the damage is predictable or negligible. And then another consequence of predictable damage is that you can use linear regressions to interpolate back to zero incident helium ion dose. So for this, you can even predict, or you can use linear interpolation to predict what the original concentration of the blood was. So that completely removes ion beam damage from the equation, basically. And here's the chart that shows the average of the linear regressions. And a few things to point out are the R squared values. So the correlation of coefficient is extremely high, suggesting a high degree of linearity, which is good. And then the consistent slope across the substrates also shows the, attests to the predictability of the damage and that we can use linear regressions. And then overall, we can see that we had a 3% sampling error across drops and substrates, and then overall sorry about that. Okay, the systematic errors are less than 6%. I don't know why it's doing. Overall, I've told you about all these great aspects of microliter blood analysis, but there are some perceived limitations with it. And the first one is a statistical argument. So let's say you're taking less amounts of blood from the body. How can this represent the full body's blood composition? So for this, we're talking about sample variability. However, there are two possible solutions. We can analyze multiple microliter drops, and even though we're analyzing multiple drops, cumulatively it will still be less than the microliter amounts. And then finally, the circulatory system itself creates homogeneity in the blood. And what this does is, so we can just avoid testing after ingesting food, for instance, and this will maintain the homogeneity of the blood. So a drop will represent the composition of the blood. So overall, we can see that HemaDrop creates quantitative results as opposed to the qualitative results, for example, of other microliter technologies. It's homogeneous compared to dried blood spot technologies, so we're getting the same spectra for different locations, the same composition for different locations. Additionally, it's resilient to damage, so we can conduct testing on the same spot multiple times compared to the dried blood spot analysis. And it's also versatile as a solid film compared to a liquid analysis. You can use multiple types of vacuum-based techniques. Thank you.
Are there any questions for Yash?
Yes.
Very nice presentation.
Thank you.
My direct question to you, can you specify which was your involvement in such a lovely project?
Yes, so originally our research group was working on, with continuous glucose sensors, the percolation of sodium ions into it. And this is essentially using, it's basically blood on a substrate, right? If there's blood on the glucose sensor. So we were trying to track this percolation. So my contribution was, I was part of the idea of, if we were looking at blood on a substrate, we can also determine the blood's composition by analyzing the substrate. So that was basically how we transitioned into blood analysis. And I've been with the research group since then. Yeah.
I do have a second question.
Sure.
In your instrument, you were saying that the experiments need to be done in vacuum.
Yeah.
How high quality of vacuum?
So it was the experiments that we did were in ultra high vacuum. So 10 to the -8 through 10 to the -11, but that was just to ensure that there were no contaminants. So potentially it could be done in less strenuous conditions, I guess.
Thank you so much.
Yeah. Thank you.
Any other questions while Hashimi is setting up? Are you sure that, with your small quantity that you can detect, very low numbers of pathogens?
Yes, so regarding pathogens, the results that we've had so far are only elemental compositions, but the power of HemaDrop that we foresee is that since it's a solid film, it can be used with a variety of vacuum-based techniques. So even using NMR, for instance, or terahertz spectroscopy, we could determine the bond energy of pathogens, and using that we could identify whether they're there or not. And then you can use multiple drops to ensure that the pathogens are there if they're not in a specific drop.
Okay, thank you.